Let's take a look at number 23 in section 5.7. We're going to use the change of variable formula to evaluate the following definite integral. So when they say change of variable, this is the substitution method applied to a definite integral. And the important thing is there is when we do that, we are changing the variable from x to u, and therefore we also need to change the corresponding limits of integration. So what would you choose for your substitution here? Well, I hope you see it. We have 2 divided by what? The square root of the quantity 9x plus 8. Again, your numbers here may be slightly different, but should be very similar to this problem. So I'm going to let u be that inner function, right, under the radical here, 2 over root, right, 9x plus 8. I'll let u be 9x plus 8. So what's the derivative of 9x plus 8? It's just 9. So I get du is 9 dx. And I see I just have a dx here. And so I'm going to multiply. I'm sorry, I don't have a dx. I have a 2 dx. That's the way I think of it. And so I'm going to multiply by 2/9. 2/9 times 9 is 2. So that gives me the 2 dx. Now, alternatively, you could take this constant multiple 2 and pull it out by the linearity properties for integration, and then you're just left with dx. And I can solve for dx by dividing by 9 or multiplying by 1/9. But when you pull that 1/9 out, what's going to happen? The 2 times the 1/9 will give you 2/9. So same thing. If you do it the other way, it's basically the same thing, and that's fine. Now, important, you have to change the limits of integration. You must change the limits of integration here if we're going to change to the u variable. And so when x is 0, what's the value of u? Well, here's the relationship. Replace x with 0. I get 9 times 0, 0 plus 8. I get 8 for u. When x is 2, I get 26 for u. And so in order to write this next step, I have to change the limits of integration. You can't have x limits of integration here. So I've got the 2 dx, which is the 2/9 du. So I pulled that 2/9 out, du, and I'm left with 1 over then the square root of 9x plus 8. Well, that's 1 over the square root of u, and 1 over the square root of u is 1 over u to the 1/2, which equals u to the negative 1/2, right? And that's how I'm going to write it, u to the negative 1/2. And of course, I change my limits. The lower limit of 0 is now 8, and the upper limit of 2 is now 26. So now I just totally forget really about this integral, and now I'm doing this one because the value of this definite integral equals the value of the original definite integral. And this one is much easier to do, right? Again, just power rule. What's the antiderivative of u to the negative 1/2? I add 1 to negative 1/2 and get positive 1/2. So I have this 2/9 out here. I'll get u to the 1/2 divided by 1/2, right, by the power rule, which is the same as multiplying by 2. So I'm going to evaluate this, right? Make sure we use the evaluation bar. Once we find the antiderivative, there is no integral sign here. All right, we're going to evaluate the upper limit of 26, lower limit of 8, and subtract. Just clean this up a little bit. 2/9 times 2. 2 times 2, that's 4/9. And then I'm going to write u to the 1/2 as the square root of u because I'm going to plug in now. And I'll factor out the 4/9, and then I'll plug in 26 and plug in 8 and subtract. Now, I'm okay with this, but you could simplify a little bit. In fact, I think this is what Achieve took. The square root of 8 can be written as 2 square root of 2, and that's because 8 is 4 times 2, and so we can use the property of exponents to write this as the square root of 4 times the square root of 2, which is 2 times the square root of 2. 26 does not have a perfect square factor. It's like 2 times 13, and so we would just leave it like that. So there's the exact value. You can, of course, check with your calculators, function integrating technique, and it's not going to, of course, give you this, but you would type this in as a decimal and then compare it. And I would go back to the original integral if I'm checking, in case I made a mistake somewhere in here. So always go back to the original integral and make sure it's equal to the decimal equivalent of this here. Okay, hope this is helpful.